So, good afternoon, everyone, again. This is a project I done last year while I was an intern at Caribbean Airlines, and this was done in partnership with them. This was also a project I did for my final year undergrad. So, at the time, the airline's business team and the IT team came together and they decided that in order to be competitive with other airlines, augmented reality was the latest innovation in terms of customer engagement, and it would give passengers and potential customers an avenue at engaging with the airline and their new app that they released. So at the time, all these other companies, Kayak, Latam, Kiwi, KLM, had just released, I don't want to say beta, but very new versions of augmented reality apps, and all of them will geared towards allowing passengers to measure or size their carry-on luggage at home. So Caribbean Airlines decided that they wanted to launch an AR application. It would have been the first AR app for the airline in the Caribbean. And at the beginning of the project, they outlined a few specific goals or specific requirements, right? So it had to be developed for either Android or iOS, and I chose Android because I had access at the time. I had access to an Android device 24/7. It had to incorporate augmented reality somehow for the purpose of baggage measurement, and it had to interface with React Native for the primary purpose that their current application is currently built in React Native, and to prevent passengers from having to download a completely separate app for this one specific purpose, it made more sense to integrate the AR part directly into their current application. So in order to implement AR in an app, I had two options: either go raw, take the direct camera output, and attempt to relate it to the initial measurement unit measurement, so that's accelerometer and gyroscope somehow, or to use a pre-existing API. So I went through Wikitude, Vuforia, React, and settled upon Google's AR Core, which had just released for the light estimation, plane detection, and point cloud mapping. So out of the box, AR Core provided a few of these basic features, and that's what this video is showing here. The mapping points to the given location and using collections of points to detect planes in the real world. The way it did this is by SLAM, or Simultaneous Localization and Mapping. So this just works on the idea that there's a high degree of correlation between estimations of various features or landmarks in space. So Harris Corner features and Canny Edge features, for successive observations in the real world, SLAM is used to assign X, Y, and Z coordinates to real world feature points with a level of confidence, so between 0 and 1. The thing with SLAM is that in order to update the accuracy of these real world points, it needs to take lots of measurements. So that kind of worked out in this case because I was using the camera feed from the device. Every time a frame was processed, it would update the location of these real world points, and hence the error in spatial location for each of these points would decrease with each successive measurement. Now, purely visual SLAM, so using just image features, tends to struggle in dynamic environments. So occlusion, shiny or transparent surfaces. So in order to increase the accuracy of AR Core's SLAM, it incorporates the IMU measurements. So it takes into account both, for example, corners and edges detected by the camera, in addition to the motion of the phone. So any sort of tilt and pan, as well as translation in space. And it would take both of those measurements, correlate them in some way, and generate X, Y, and Z coordinates for real world feature points, again, with a given confidence level. So the idea was to take these real world feature points, generate a convex hull around a bag to be measured, and then generate a minimum bounding box about this convex hull. So in order to measure the passenger's bag, I would take the measurement of this minimum bounding box for the width and breadth of the bag. And in order to get the height of it, I would just take the height of the highest point measured. However, in order to generate that convex hull, there was a problem where the app would pick up almost every single point it tried to scan. So at one point, it was picking up points around a bag, for example, on a fluffy carpet. And this was contributing to errors in reading the dimension of the given bag. At all points in time, it would pick up points 10 feet away from the bag that had nothing to do with the object I was trying to measure. So I had to figure out some way to filter these points. Now, in order to filter these points, the first thing we tried was using a centroid. So when a passenger points their phone at the bag, it would start filtering points about that initial position. However, there were a bunch of edge cases where a passenger doesn't actually start trying to measure the bag with the phone pointed at the bag. So I switch on my phone camera and have it hanging at the side of me, and then decides to point it at the bag. So that was a host of new problems. So in order to work around that, we incorporated having passengers just place a 3D virtual object. So for example, in the video here, they can place the object on the ground and only points within the proximity of that object would be considered. So it would handle the edge case in which a passenger is trying to measure a very, very, very large object where the object doesn't actually fit in the frame, because it would still generate a measurement that is too large to be handled by a standard carry-on bin. And it would also handle objects that can fit into the 3D object being placed and filter points accordingly. So in order to actually generate that convex hull, there are quite a few algorithms, both in the 2D and 3D space, for generating a given convex hull. There's Graham Scan, JavaSmart, Quick Hull, which is the one I ended up using for two main reasons. One was the ease of implementation on an Android device, and two, because it operates in O n log n efficiency. That's the amortized runtime. There are weird edge cases when it can go to n squared. However, for the purposes, most of the times it would run in n log n. This is a brief overview of Quick Hull. So it's essentially find the points with the minimum and maximum x coordinates. So these two, divide all the points up along this line, and because these will always be part of the convex hull, use the line formed by the 2 points to divide it into a subset. So the upper set of points here and the lower set of points here, and it works recursively. So it constantly finds the most extreme points and removes any points that lie below the line connecting the extreme points. So it removes the need to compare the distance of all the points inside here, and it generates the convex hull of your input, of all your input points. It just keeps on doing this until no points are left. So at the point at which no points are left, the algorithm terminates, and the points that were selected end up being the convex hull. From this convex hull now, to actually find a minimum bounding box, the rotating calipers algorithm by Rock is used. Now, there's also a 3D version of this, which attempts to fit a minimum bounding polygon in 3 dimensions. However, at the stage, just pulling the maximum point mapped to the given object was working fine in terms of accuracy, and the computational complexity of implementing the 3D version of the algorithm, the trade-off there wasn't worth it. So in order to let users know whether or not their bag would actually fit into carry-on, because as a point of this project, a passenger would size their bag using the app, and it would tell them whether or not it actually fits in the overhead bins, right? We juggled a few different options. The first one was to spit out the dimensions of the actual bag, similar to how Kayak had implemented their app. there was another option in which we just display text on screen. However, we settled upon a combination of both. So the 3D object placed would change color depending on the size of the bag. And a text prompt would also show whether or not their bag actually fit. We didn't see the need to actually display the measurements of the bag to the passenger. However, it is there in debug logs for the purposes of accuracy testing. So this is a demo of one of the use cases. So for example, I'm trying to measure a backpack here, rest it down and walk around the bag. And since this bag does indeed fit in the carry-on, the 3D object placed will change color. However, there were quite a few challenges in terms of measuring the points. So in order to map points on a shiny or transparent object, an issue was that points reflected off of the shiny object and points that lay behind the transparent object was also being considered in calculations. So for example, if I have a block of glass, it would map points 10 feet behind the block, or if I had like a mirror, it would map points reflected off of the mirror behind me and attempt to measure that instead. However, the point filtering that was previously implemented sought to solve this problem because it enforced a hard limit around the place object for which points can be measured. So any of those points that are really far away behind me would be filtered out, and any points that are directly behind the object past a particular threshold would also be filtered. Currently open problem is dealing with especially these ring-like objects. In testing, for example, the common case was a closed basket or an empty market bag. The estimates for the dimensions of really thin-walled objects or really thin objects overall, owing to the way by which ARCO maps its features, which is a combination of canny edge detection and Harris corner mapping, the measurements for these type of objects are inconsistent. Ironically, a few weeks after this project was completed, ARCO released the Depth API, which could possibly aim at increasing the robustness of the app to measure these objects. So it would dynamically map similar to how LiDAR works in producing a depth map upfront. However, not to the same accuracy at which LiDAR works because it uses this same exact method, is SLAM, without any sort of radar mapping. So that brings me to the end of this presentation. I'll be accepting any questions, and thank you
all. Thanks, Aadidev. Nice project. So did they end up using it, or it still needs refinement?
So at the time at which I finished this, the entire pandemic started, and we didn't really get, the only thing holding this back is development on the iOS side, since this is only an Android. So it wasn't implemented because of that.
Okay. One other thing, so here you're looking at kind of fixed dimensions, but I know certain items like a duffel bag, it goes based on the sum of the dimensions, right? So is that something you can handle as well, or? So
there's the option to choose 3 different types of bags. A personal item, I should have probably recorded that too. A personal item, a carry-on, or the duffel. So the duffel wouldn't be standing up like this. It would actually be lying down with the longest dimension parallel to the ground. So it accounts for those bags that aren't typically carry-on. So that's how we worked around that problem.
Okay. Nice, thanks. No more questions from me. Yeah.